I think one of the really, biggest bottlenecks when it comes to extending generative AI from text, from images, from video is really a bottleneck of data scarcity. For example, the amazing success of diffusion models for generating images hinged on the fact that we had billions and trillions of real world images that we could feed into the training data to train these generative models. At this stage, we do not have that for 3D worlds.
Hi everyone, welcome to the first episode of Inside ALLSIDES, the podcast about anything 3D and AI. And I'm your co-host actually, Franz, co-founder and CEO of ALLSIDES.
Yeah, I'm Burkhard, co-founder and CTO of ALLSIDES.
And today we have the pleasure to be joined by a fantastic first guest for our podcast, Professor Daniel Cremers. For those of you who don't know him really well, professor in computer vision and AI at the Technical University of Munich, a true pioneer and expert in this field, and also the director of the Munich Center for Machine Learning. Welcome, Daniel.
Hello, Franz. It's a pleasure to be here.
Maybe for those of you, we of course are big fans of you and we have been working together for quite some time. But for those of you who don't know you that well or your contributions to this field, maybe also your life as a researcher and entrepreneur, maybe just in your own words to introduce yourself, to get the audience up to speed, that would be amazing. Thank you.
Thank you, Franz. Yeah, I've been in the field of AI for the longest time, since the late 90s. Actually, it's when I started in AI. I studied physics originally and then moved into artificial intelligence after my studies in physics. And so I've been in the field for a while. I've been a professor in German universities for more than 20 years now, 21 years actually. Initially at the University of Bonn and now for around 16 years at TU Munich. And I also engage in a lot of activities over the last years. I've built a lot of competence centers like the one you mentioned, the Munich Center for Machine Learning. I've also initiated the Munich Data Science Institute, where I'm one of the directors. And then there's also the ELLIS network. This is a European network of AI competent or machine learning competence centers. And I'm one of the directors of the Munich unit of this ELLIS network. Initially, I really focused on research, academic research, writing publications and stuff like that. But with the years, and especially in the last decade, I've shifted my attention more into also building startups and doing technology transfer. Because I came to realize that a lot of the things we develop in academia end up in publications, and these will tend to just collect dust in some library. And if you really want these things that we do to impact the world, you have to support the transfer into real world technology and products.
Yes, and I think that's one of the aspects that surely has drawn me to this field, and I've been working in it for the last 10 years, that academia and also the world of technology, startups, are so closely interlinked. Basically, what is happening maybe in 1 year or in the next year can be applied and have a real world impact. I think that's fascinating and very difficult to see in other fields happening. And I think that is also, if you look lately at our space, right, there's lots of talk about world models, spatial intelligence, physical AI, for those that have been following very closely. How do you see these developments, and do you think we will see similar things happening or similar traction than what has been perhaps happening for the past 3-4 years in text, image, the video when it comes to AI?
Yes, it's a fascinating question. So the field of AI, as long as I've been in it, it's been moving fast, but the pace has picked up dramatically over the last years. The innovations we see coming around from one year to the other, things just accelerate dramatically these days. It's quite impressive. And one of the big hot topics, you mentioned it these days, is generative AI, foundation models, world models, and both for language, text, but also for images. And increasingly, this is something I see coming on the horizon for 3D. This is a big hot topic where we see a lot of efforts both in academia and in companies to make that happen, to develop generative models that are able to create and hallucinate entire 3D and possibly even dynamic 3D worlds.
Yes, absolutely. And one could, of course, argue, and lots of incredibly smart people, researchers, entrepreneurs are contributing to this space now. Lots of money flowing into this. NVIDIA, of course, making a big push into the world of physical AI. Now we see world models combined with robots, like a lot of exciting things, I think, that are happening on a daily or weekly basis, like we got used to now in AI anyway, right? And it's also a very complex world, right? 3D inherently is more complex than maybe just plain text, image, or video. It's perhaps a better representation of the world, but also tougher to pull off on various different levels. What do you see some sort of the developments that still need to happen, or let's say where lots of researchers and founders, developers should perhaps spend their time on in pushing the space forward?
It's a very good question. So I think one of the really, biggest bottlenecks when it comes to extending generative AI from text, from images, from video, where we've seen great successes, to 3D worlds is really a bottleneck of data scarcity, right? For example, the amazing success of diffusion models for generating images, super, photorealistic images of pretty much anything. This great success hinged on the fact that we had billions and trillions of real world images that we could feed into the training data to train these generative models, right? And at this stage, we do not have that for 3D worlds, right? And as a result, a lot of people try detours, right? They try to generate 3D worlds through image and video synthesis, because you have training data for images, you have training data for videos. So you generate videos, and then in a way, the current strategy pursued by tools like Sora, OpenAI, and other companies is to somehow generate images and videos and then sort of keep your fingers crossed that the resulting worlds that you see in these videos are 3D consistent. But the truth is they're not, right? There's lots of studies that show the generated videos generated by tools like Sora, they look very photorealistic, but if you check, they are not 3D consistent, right? Because these algorithms do not understand 3D. They only understand 2D. They were trained on 2D. And somehow this inherent 3D structure doesn't naturally emerge, apparently, if you just generate and train on 2D. So you really need 3D data, high resolution data at massive scale to train 3D generative AI methods. And that for me is the biggest bottleneck. And in fact, that is where AllSides is really excellently positioned, because you guys are creating amazing high resolution 3D content at massive scale, right?
Yeah, that's a very interesting take, Daniel, for sure. So, I mean, we see it in a similar fashion that there are those famous examples of where the geometry of the generated images are just not aligned with realities. But in the same way, we also see it for material properties, that there are some unreasonable materials. So for sure, working in the 3D space can overcome some of that, and at least could be a component for solving this. Now I have another question. Your work on variational methods and also direct methods like famously SLAM. I mean, this was foundational in the area of 3D reconstruction. Now the world of 3D reconstruction is slowly moving also towards more photometric aspects, so not just pure geometry. So how do you see that, and also how do you see the challenges that arise from there in representing appearances, also material properties, and what do you think is still left to be done in that space?
So Burkhard, you're totally right. I think there's a huge shift in computer vision over the last years, moving more and more towards 3D. For the longest time, computer vision stuck to images, to 2D images, right? And even in applications like self-driving, they would detect cars and pedestrians and cyclists in images, right? With 2D bounding boxes identifying them in the image. And for years, I've been arguing this is not what we should do. For the cars to really understand the world they move around in, or humanoid robots that we see coming more and more, for them to understand the 3D world, they need to process 3D. They need to reason and understand and detect things not in the images, but in the world that is behind the camera. And this has been overlooked for years. And I think to a large extent, it wasn't done because people didn't have the algorithms to generate the 3D world from cameras and videos. And we laid a lot of the foundations, as you mentioned, with the SLAM methods like LSD, SLAM, and DSO that enable you to just take an off-the-shelf camera and walk around, and in real time the whole 3D world emerges at massive scale and in high resolution and densely. And so that, I think, has revolutionized to some extent what we do in computer vision. And it revolutionized application areas like self-driving cars, where companies like Tesla can now focus and depend on the camera to process the 3D world rather than a LiDAR scanner. Because you now, with the techniques that we and others developed, have the tools at hand that take a camera input feed and spit out the 3D world that is observed. And then you can do reasoning about 3D. And you're right, we for many years focused more on reconstructing the surface of objects, right? Whereas what you really need when you go into autonomous robots, humanoid robots, for a robot, it's not enough to extract the surface of the world. It needs to understand the material properties, right? Can I grasp this glass? Can I grasp this bottle? How tightly can I grasp it before it shatters, right? For that, you need to understand what are the material properties of the object in front of me, right? And this is super difficult, right? The reflectance properties, the the physical properties of an object. We as humans do it all the time. If you see a bouncing ball, you not only see the shape of the ball, but you essentially see the physical properties of the ball, the elasticity and the weight of the ball, all of this. If I throw you an object, you need to anticipate in real time what are the material properties for you to grasp it and to catch it and to hold it. You need to estimate the weight. As humans, we do that all the time. We look into this world and we don't see just the surface of the world, but we see the underlying physical properties and phenomena. And this is something where computer vision dramatically lags behind. We, in 2020 at CVPR, we published a paper where we showed that just from a video, a machine can indeed infer the physical properties of the object that is bouncing around. Let it be a tennis ball, or let it be a teddy bear that falls to the ground. And by looking at how it bounces off the ground, we can see how rigid, how deformable is the teddy bear, right? And this is for me, has always been the driving paradigm, or the driving, let's say, motivator for all I do is this idea that if a human can do it, so should the machine.
I mean, that's a fascinating take on this. So, like, that deriving all the physical properties of an object actually from a video, right? So that I mean, that is the great goal to have, to envision for the future. How important do you see these aspects? So going beyond like just visual representation of an object, but also having maybe the friction of the material, having the articulation of an object. You mentioned it. How it compresses, the weight, and so on. How important
I
do you
think
see this for robotics training specifically? Because we believe this is a hot topic in the future, training robots end to end in simulation. And like how do you see it? Which are going to be the important aspects for robotics training?
I think
How do you
there are
think that?
many challenges in the field, and sometimes people get fooled, right? They see novel view synthesis results generated with methods like neural radiance fields or Gaussian splatting, and that will make you believe that we've solved the problem, but we're far from it, right? Humans can go to a table and they can grasp a glass, right? And they can immediately detect the shape of the glass in 3D. To date, I am not aware of any computer vision algorithms that can do that, right? That can capture the translucency of things in the world, that can capture very reflective properties of objects. And how to do that from very sparse data is for humans. I don't know how they do it, right? To a large extent, I don't think that the human brain really can simulate the entire physics of light transport through material, not in real time, but we somehow have learning based approaches to capture these phenomena. And I think a big challenge is in the development of these algorithms that can reproduce that. We need data. We need ground truth regarding what are the reflectance properties of the material, the translucency, all the different, the BRDFs, right? And for that, we need technical setups that are able to capture things at high resolution in great detail. And we are developing a lot of algorithms and have been developing for reconstructing surfaces, for reconstructing reflectance properties from images. And that these we showed, once the better you can recover the reflectance properties of the surface, the more accurate will also be your surface reconstructions, right?
Yeah, for sure, surfaces and reflectance properties are linked because if you look at it, ultimately reflectance is just microgeometry. So I mean that there's a direct link there. Yeah, and you mentioned also volumetric data. It is
Yeah.
like volumetric representation of objects is going to be increasingly important. Um,
That's a big important topic. People also overlook that in sciences in general, and in particular in 3D computer vision, a big question revolves around how do I represent the things that I care about mathematically, right? How do I represent 3D shapes? And the truth is, there is not one representation that serves all purposes, unfortunately, right? That would be great. But we have point clouds, we have meshes, we have sign distance functions, we have volume occupancy, we have spline surfaces, we have circles and other types of representations for 3D objects. And indeed, depending on what it is that you want to do, one or the other representation will be the right one. And for me, the fascination with the 3D world is a very long standing one. I think one of my first papers in the field I published around 2004, I think, and that is 22 years ago, and it was focusing on can I reconstruct the surface and the illumination that illuminates the surface just from images. And I think we humans, we somehow implicitly do all that, right? We don't have to check where is the light source in the room to be able to recover 3D shape. We just do it magically, right? All in one. And how to reproduce that in a machine, I think there is still need for better algorithms and better tools. And all these problems are far from solved.
Certainly, again, very good insights, and some of this translates for sure to entrepreneurial, let's say, takes as well, with many companies being started in this field. Where do you see some of the, let's say, more imminent applications, perhaps? Because of course we talked about robotics, and there's a common understanding that it's of course great for the field, that lots of great people working in it, lots of investment is happening, but it's also, again, for many wide-ranging use cases, a tough problem to solve, and we will work for many coming years on solving this, right? But where do you see some of maybe the most imminent impact of the latest developments in this broadly defined space of, let's say, 3D AI, which also then includes text to 3D or image to 3D. Where do you feel like the end consumer or anyone really that has been using perhaps ChatGPT or Claude right now might also get exposed to some of these techniques that we have been discussing in this call?
So there's a lot of application areas. You mentioned robotics, and that would include, on a more short-term scale, autonomous cars, right, that need to recover the 3D world they drive through in order to be able to understand it, to anticipate what's going to happen next, to reason in 3D, right? All of this is necessary for self-driving cars, but also on the more long term for humanoid robots that will need to move around in even more confined spaces, in houses, in buildings, and will need to reason about 3D in order to get from any place to any other place in a reasonable manner, right? Or to grasp and interact with 3D objects, they need to get both the shape of the objects, but also the material and physical parameters of the world. But on a more immediate front, so one thing is generating 3D worlds, for example, for advertisement purposes, right? Or for the whole movie industry, for that matter, right? Already now, people work a lot with blue screens, green screens, and then they generate the 3D content around it later on. But how to do that in real time or with a generative AI, a controllable generative tool that will generate the 3D world that you want in your movie, in your video clip. And there's powerful developments happening. Companies like World Labs and also here in Munich, we have companies focused on spatial intelligence, spatial reasoning. We do a lot. For example, we have a startup that we founded at TU Munich called SE3 Labs, and that startup does autonomous drones. And these drones also need to reason and understand 3D worlds, right? And so it's all about processing, understanding the 3D world and being able to generate it. But the big challenge when you create generative tools is to validate how well do they work and to train them. That's the two things where we need data. 3D data, 3D content in order both to train a generative AI, but also in order to evaluate the performance. How good is the 3D world? How well does it match the real world, right? And for that, you need to have the real world. You need to measure the real world. And that's in particular what like ALLSIDES is doing, right? Is measuring actual 3D objects from the real world so that you can connect to the virtual worlds that you hallucinate.
Yeah, we of course totally agree with you on that one. That's why we're so bullish on our future here. One thing I want to maybe conclude with, just to tie back to the research side of things. Of course, you work with a lot of young, brilliant students coming from various fields to do either some master's degree or PhDs with you, postdocs, and so on. Where would you say are some of the exciting gaps that young researchers could focus on or work on in this field to leave a mark on the research side and really help advance the space?
For me, I think on a fundamental level, one of the biggest challenges in research in computer vision, and in particular 3D computer vision, is how to connect between the more classical optimization-based methods and the more recent learning-based approaches, right? Because in the end, you want to bring together the best of both worlds. Classical methods are often amazingly good at just getting from measurement data to a representation of the 3D world, the movement of the camera. And we've developed many, many classical optimization methods to do it. And now increasingly you get learning-based approaches that are extremely powerful at essentially hallucinating 3D worlds, but how to connect the two, how to hallucinate 3D worlds that are actually consistent with what you see in images and videos. This requires both the optimization methods capability to couple to sensory data, but it also requires this component that can generate or hallucinate based on training data. And I think this is the gap we need to bridge in order to arrive at a performance like humans have it, or maybe even superhuman performance, because humans are able to hallucinate things, right? If I only see part of a person because in a Zoom call the camera only sees half of it, I can hallucinate the rest. Why? Because I've seen a lot of humans and I know what they look like. And this capability of humans to hallucinate whatever is not observed, this can be reproduced with generative AI, but you really need to connect the two. And that's one of the directions that we're pushing forward in massively, combining classical and learning based approaches to reconstruct and generate 3D worlds.
Yeah, thanks for that. Hopefully, lots of researchers are listening to us as well, who want to leave their mark, and now they know exactly what to work on. But yeah, having said that, we're just very thankful that you joined this conversation, Daniel. We couldn't have hoped for a better partner in our first ever podcast, and hopefully, this is the start to a great, conversational adventure for the both of us. And hopefully, we can have you back in the future, Daniel.
Yeah, thanks,
Thank
Daniel.
you, Franz. Thank you, Borgard. It's been a great pleasure chatting with you.
More such conversations are coming in the next weeks and months with researchers, developers, entrepreneurs, and investors in this field. And we're looking forward to many more such conversations. Thank you.